Okay, hello everyone. This is the workshop for module 7. So today we're going to cover quite some things. The first is the generative design product activation, which most of you, I believe, have already done. The second is a quick example on how evolutionary algorithms work within generative design, which is the new tool we're going to be exploring for the remaining weeks of the quarter and for your final assignment. We're going to go through some examples, and then for the Grasshopper folks, I'm going to share some links and some tips on how to do that. So to start, the product activation is quite simple. You first need to go to Autodesk student. So you're gonna Google that. There's several ways of going into the student website. This is the quickest one. And basically you wanna go to down here, when you see all the products, you wanna go for Revit Generative Design. Please keep in mind that you need at least Revit 2021 or earlier. And then you click Get Started. So you're gonna log in. And once you're in, you'll be able to activate your generative design permissions. So here it's telling me that I'm confirmed because I'm with the student license. So I'm going to click Get Software. Looks like it's only showing me some products. It's probably because I already have my generative design product activated, but essentially what you want to find is this icon that we saw earlier that says Revit 2021 generative design, and you want to click on Get Product. Basically, after you signed in, it should be good to go, and you should get like a PDF saying that your product has been activated and that you're ready to go. So with that out of the way, let's go into the slides again. So yeah, evolutionary algorithms. So there's many types of algorithms that generative design uses. Basically, they do non-dominant search, such as NSGA2. And how this works is basically we start from a random or initial population of models which have some sort of fitness function. So the whole principle of this, and if you've looked at the assignment, the generative design framework is basically oriented towards this 6 components. The first one is the objective. What do we want to study with generative design? The second one is the model. So how do we translate these design questions to Dynamo or to our geometry? What types of elements are we modeling? Our design variables or our inputs can be both variable or constant. Our outputs, which are the evaluators, will tell us how fit or high performing our model is. And after we run the generative design framework, we need to do some interpretation of the results as any other simulation we do. So going back to the evolutionary algorithms, so we start with a population 0 or a generation 0. This is like the initial conditions of the study, and then we're going to evaluate that fitness. From that evaluation, we select the best individuals, and there's 2 strategies to obtain the best, which is crossover and mutation. We'll see that later. And after doing this repetitive process, we can either stop the simulation by number of generations or by a fitness goal. So once we reach a certain fitness, the process will stop, or once we reach a number of generations, it will stop. This is a very simplified diagram of how it works. So to show you guys a better example, I found this online and I think it's very illustrative to show you evolutionary algorithms. So imagine you have a backpack and you're going on a flight and you have a maximum weight of 3 kilograms. So that's the max you can have in your backpack. And you have 6 items that you could include. You can include all 6. You cannot add all 6 of them because they exceed 3 kilograms. So you have to choose which are the ones you want to take. So each item has a weight. That's a constant. Each item has a value in terms of how important it is for you. So in this case, food, this thing, the pillow thing for the plane, and your computer is the most important items, and maybe water is not that important because they'll give you in the plane. So this is just a quick way of giving priority to some of these items. And then the variable that we're going to deal with here is if we include it or not. So let's say each backpack or each generation will have a bunch of ones and zeros. So in this case, we're including the laptop, we're not including the water bottle, and we're not including the pillow, but we're taking headphones, iPad, and food with us. And let's say we're going to do that randomly. So we're going to start with our first generation of backpacks. So for example, this one here doesn't have the headphones and the pillow. This one doesn't have the water bottle and the headphones, I think, and so on. This one only has 2 items, for example. And then we have our goals and constraints. So our goal, of course, is to maximize value and staying within those 3 kilograms of weight. So the next step is we rule out those generations that exceed the weight. So that's pretty easy to spot, and we're just going to remove those. And then we're gonna take the best generations, the higher performing ones, because they scored more points in terms of how valuable each item is. So we're going to take these 2 items, and that's where we're going to start our next generation. So going back to the flow chart here, we start with a random generation. We have evaluate the fitness and select the best individuals. So in between, we're ruling out those that exceed the weight because those are no-goes. And then we're going to do 2 techniques that will make us have a new population, which is crossover and mutation. And that is fairly simple. So we take our best individuals and we take their gene pool, which is the ones and zeros that tell us what they have and what they don't have. And the first technique that is commonly used is called crossover. So in a arbitrary position in the chromosome or in the parameters that tell us what's included or not. Hi, you're in 220C. So we're gonna cut the number of included or not included, and we're gonna flip them with other generations. So this is just adding some random effect on our initial generation. And the other technique is called mutation. So it's basically tweaking each one of the variables randomly as well to see if we get a better result. So by using these 2 techniques, and there's many more, we can get another set of backpacks, which will probably perform as equal or better as the 2 highest performing of the best of the first generation. So that's just a quick example. There's many more, information out there. There's papers. If you want to research more into this, the algorithm is called NSGA2, which stands for non-dominant gene sorting algorithm, I think. So yeah, that's kind of how generative design works. But this is just the surface. What generative design really does is that it helps you to come up with thousands of design options, and it's supposed to be an aid in the design. It's not supposed to replace the designer. But actually help them to come up with better designs. So for that, I'm going to show you the views in the city example. So some of you might have already seen it. It's basically a model that, hey, it's a model that plays around with the location of the building, and it evaluates its performance based on the number of unobstructed views to the outside. So yeah, so let's look at that through the lens of generative design. So I think this is quite relevant for your next assignment, because we're asking you to think of problems in a certain way, which is what's the question you want to answer, what are the trade-offs that you want to study, and how that translates into a model. So what are the inputs you're going to use, what's the model going to look like, and what's the outputs that you want to maximize or minimize. So that's exactly what we're doing in this example. I'm just going to show you how to set up generative design in Revit. It changed a bit from last year. So if you have seen the recordings, there might be some differences. So just be aware of those. So first step is, if you have a script that relies on a Revit model, they always have to be linked. I think this is pretty obvious at this point. So for views in the city, I have a Revit model that has existing geometry. So I'm going to keep that open. And then I'm going to open the original script. Things to keep in mind is your script shouldn't have any warnings when you're running this type of studies. You want them to be clean, pretty understandable in terms of the logic. So, and basically the most important thing is that you select inputs and outputs. So our inputs in this case, as you might recall, are the coordinates in which my building will be located along this inner rectangle, and the total height. So just make sure when you right click each one of these sliders, they're selected as is input, because this will allow you to manipulate it through generative design later. And same when you go to your outputs. So in this case, we only have one output. Make sure it's a number. Make sure you've rounded it up so it looks clean. Outputs should always be integers or doubles, but just make sure it's just a number, and plug it to a watch node. So this is a watch, and then you can change the name to, so it shows like what you really want to evaluate, but this is a watch, yeah. And yeah, make sure you right click and you select is output so you can see it later. That's it. Once you've done that and you run it, there's no warnings. This is how you create a study. They keep changing this year by year, so I literally just figured this out. Before, it used to be you go to generative design and there was an option here that said open generative whatever. Now it's down here in extensions. So question, has Glenn covered this? No? Okay, so this will probably be helpful. Again, once you run your study, your graph or script, I call them script, some people call them graph, you go to extensions and you need to make sure all of these show menus are sorted. So I'm going to start with documentation browser. Basically, this is telling you what's happening in your script. But that looks good. Then we're going to go to show graph properties. Here's where it gets like important. You need to give a name to your script, to your study, sorry. So here I'm going to say checks for unobstructed views to the outside, whatever. I'm going to select an image that I previously prepared for this. So it's just a screenshot, so I know what type of study this is. My name, URL if you want to have some followers on LinkedIn, And yeah, that's it. So I'm going to save that. Second check I need to make is the show graph status. So this one is important because this will tell you if there's a warning or an issue in your graph. So it looks like there's no issues here. If there was one, it would be telling me, oh, fix this, or you don't have inputs, or you don't have outputs, or your output is a string or something. And the most important thing out of this workshop is this, clicking here, generative design, because this is going to make your graph go into the interface of exploring studies. So clicking here, oh, there's one issue. Okay, so it says nodes in a modified state are not allowed in this graph. So looks like I need to run my graph. So I run it. Cool. So looks like there's no more issues. That was it. Now, how do I hide this? Okay. Now I will save this again, and I'll check the final check I need to have here. And this is the packages. So in case you guys have a random package that you use, like Lunchbox or one of the shady ones that are out there, it will tell you if there's an issue with the package. So in this case, I'm using pretty straightforward nodes, nothing special. The only thing that you need to remember is if you're calling geometry from Revit, remember to have the data remember node. So in this case, the lines that I'm calling from Revit are being remembered in my study. These are the property lines. And the masses of the buildings are also being remembered here. So all of these are the surrounding buildings as solids. And I need to remember those because generative design is going to iterate hundreds of generations, and it needs to keep the same geometry. So far we're done. Now, if we go back to our folder, we should see a new folder that has been created by Dynamo that is called the name of our script .dependencies. So this is kind of like a repository of our script. It's kind of our scripting code. So we're gonna keep that there. Don't delete it because this is needed for the study. So now that we've checked all of our boxes, let's see what's next. So yeah, first we need to check all of these shows. So make sure that the graph is working, give the name, make sure there's no warnings, save, and then we create the study. So we can create the study from Revit or from Dynamo, it's the same thing. So in this case, I'm gonna go to, let's do it from Dynamo because my modeling is happening on Dynamo. So I'm gonna go, hi Glenn, I'm gonna go to, yeah, it's working. Okay. So yeah, now you're gonna go to create study. So any questions so far? Okay. So when you first open this window, you might not see the right folder here. You might see some examples from Autodesk. Actually, that's a great, if you have questions, make sure you check this before you start doing especially your final project. Autodesk has great examples out there, and they shape their examples so that they're nice looking. So don't be too, scared to do this. For example, the office layout. That's like their fanciest example that they showcase all the time. So just get some inspiration from their examples. They have the files here if you want to download them. So yeah, make sure you connect the folder you're working on. So in this case, it's my module 7 folder, and then you can select it from here, and you'll see the study we just created. This is the screenshot I added. This is the description that I added. So I'm gonna click on this, and then this is where we define our study. This is the study name. So this is workshop module 7, 2022, let's say. And then we start by defining the method. So this is really cool, and I encourage you to play with this. There's 4 ways of running your generative study. The first one is I'll start by randomize. It's the most straightforward. It's basically taking your inputs and you've defined a certain range for them. So you've defined in your slider over here. Let's see if I can show you. So these are my inputs. By the way, if you see the name refinery, that's how the product used to be called a couple of years ago. They changed it to generative design, which is harder for me to pronounce, but yeah, it's the same thing. So in our inputs, we've defined some bounds. So this input goes from 0 to 1, every 0.1, and so on. My inputs have some ranges. So the randomize option will pick random spots within that range to create a new model, and it's going to evaluate my outputs, which in this case is my evaluator here of the unobstructed views, right? The site evaluator. So when I select randomize, I'm going to select then the variables and constants that I want to include in my study. So let's say for the very first study, I don't want to include height. I want to set the height to 21 units, and I'm going to vary the UMV coordinates in my property space. And then the goals is, sorry, in randomize, there's no goals, because in randomize, we're just studying the entire design space. We're just selecting how many generations we want. So in this case, let's do a little more. Let's do 8 generations to see what happens. And we click generate. So this is where the magic starts to happen. So in the left, you're going to see previous studies that you've been running. So these were some that I was running before the workshop. And this is my current study. And yeah, it's going to take a while. But hopefully in a couple of seconds, we will see some stuff popping up. So as this is creating all my alternatives, I'll go through the interface from the Explore Outcomes menu. So there's 2 things that are happening here. First, we created our study. So for those that prefer Revit, here's where you access it. There's 2 ways. You can create your study first, and then there's a separate window to explore those studies. So this is the one for exploring those studies. And there's 2 ways of visualizing your results in terms of a parallel coordinate graph here, which I think is very useful in case you wanted to filter out some solutions, if you want the better performing options, or let's say you just want to look at one half of your property line. How do I clear filters? And the other option is the scatter plot, which is better for when you have hundreds of generations, which I hope you will have. And then you can play around with how you display data. So for example, in this case, if you remember, this is my U axis, and this is my V axis, or XY, same. So I could graph this kind of space and then represent the evaluator using the size of the bubble. So to do that, I'm going to go and select this to be U, this to be V. And then for the size of the bubble, I'm going to click on Site Evaluator. So this will help me find patterns. So for example, I see that at the very corner is where I have better performing buildings. In the middle is kind of low. Or if I wanted to look at one particular solution, So you can see here some interesting behavior. There's like 3 clusters of performance. Most of them are in the low end. So for example, so when I filter this, I can select the actual generation, and then I can zoom in a little bit here and study what's going on. So clearly this is right in front of the tall building, so the site score will be pretty low. But if we look at the highest ones, of course, well, they have pretty decent height. Probably that's why they get better scores. So yeah, this is just a way to explore that. So I think this is pretty straightforward. Let's move on to the next study, because I think this will give you plenty of ideas to play with. For the rest of the course, the more important thing is that you focus on your idea, not too much on the modeling. So try to solve something that you really are interested in from your field. If you're structurals, or I don't know, just do something cool. So the second example it's very straightforward. So we already covered this one using the city. The second example is a super easy way to test this, and it's a tiling problem. So I'm just gonna go through the script because I think it's really, really cool. If there's any questions, let me know. Okay. So for the tiling, basically we start from a rectangle here, and the problem is, or the challenge is, we want to find out what's the size of the tiles and the orientation that will reduce the cutting and the trimming of tiles. So this is actually a very common problem, and I think it's very practical as well to see. So what I'm doing here is, and the deployment of the code is up to you. You don't have to follow any of this way of doing code, but I'm just going to show you how I started. Okay, so I start by building a rectangle. I'm going to run this just so you see it. So I start by drawing a rectangle, and then I create a surface out of that, which then I will panelize. In this code block is where I'm plugging in my inputs. So my inputs are the length and width of my tile and the angle of rotation. And in this code block, I'm creating a grid. So basically, I'm just going to show you how that grid looks like. I'm taking lines and I'm projecting them according to that tile length and width, and I'm just extending it through the entire workspace. And then I rotate it if there's an angle to rotate. So for example, let's see it here. I'll just move this around. Hopefully it won't crash. But if I change my angle, the entire tiling solid will rotate as well. And also if I make my tiles bigger in the width, this should update. And if I made them thinner, so that's kind of where it starts to cut my original surface, right? So this is kind of straightforward. You can also do it on code, and you can take pieces of this code if you need. After that, I'm doing a surface subtraction. So I'm taking my original flat rectangle and I'm cutting it with the grid, and the resulting pieces of tiles, I'm just measuring their area, and I compare the area with the original supposed area of my tiles. So if my size of tiles was like 10 by 10, the original area should be 100. If my actual tile is 70 squared units, then it was trimmed. You see what I mean? So for example, if I'm measuring this one right here, you'll probably have almost the entire area based on the tile width and length. But if I look at this, for example, it has a piece that was completely trimmed. So the area is going to be smaller. When the area is smaller, I'm going to pass that through a Boolean mask, which will allow me to split between the complete or untrimmed tiles and the ones that I trimmed. So this is just filtering out, I'm coloring them. And that's my model, essentially. So again, my inputs are tile width and length and angle. My constant is my surface because it's unchanged. The model here is creating this grid solid that cuts my original surface and then allows me to split into complete tiles and incomplete tiles. And at the end, I have my outputs, which evaluate my actual generation. So the first one is the area of my trimmed tiles. So I'm just taking all of these red guys and getting their area. And here's where I mentioned, make sure to sum everything and round it so it's nice and compact. And then I'm showing it as an output in a watch node here, which is selected as output so I can see it in my generative design window. The second output is the tile efficiency, which I defined to be a percentage using the number of the area of the completed tiles minus the trimmed over complete. So it's like a percentage of how efficient is my pattern. And then on trimmed tiles, the number of tiles that are complete. So I'm just counting how many surfaces are passing through out of the out in the mask. And the last one, I think it's a cost per tile. So I just came up with this function, which basically it's just doing, the smaller the tile, the more expensive it's going to be in terms of installation, transportation, and all of that. But you could easily just do a linear equation here or whatever. Because I wanted to explore that trade-off. For example, the question here would be, how much more money am I willing to spend if I'm reducing my waste? Or at what point is the waste more expensive than the tiles that I'm using or the extra cost? Like there's many, narratives that you can take here. So I have 4 outputs. I have 3 inputs. You can have as many as you want. I think for units it changes, but yeah, it doesn't have to be that way. If you find only that you need 3 inputs or 3 outputs, you can argue that that's all you need. So that's our model. It's straightforward. It doesn't have to be a complex script with custom nodes. I actually advise don't use custom nodes now, because custom nodes are very slow to debug, as you all have noticed, especially Anto. So yeah, I'm going to save this graph, and then I'm going to click on all the shows to see that everything is working. So the first one is the most important. Remember, the graph status needs to be generative design. I need to run the thing in manual to get rid of this warning. I'm going to save this. Then I'm going to add the name. So trade-off between waste and cost, for example. I'm going to add the image. Okay, good. Save. Documentation browser. I think we don't have anything. References, anything? Okay, we're good. So I'm going to close all this. And now we're ready to do our study. So again, create study. And this is the one we just created. For this one, I want to I'll show you how cross product works. So cross product basically takes each input and out, so each type of input, and defines a number of variations for each, and it just crosses everything with everything. It's like a lacing in here. So let's say we're gonna, so yeah, this is basically the number of outcomes that we're gonna have. So let's say I'm gonna have, actually no, this one is probably more interesting to randomize. So we see the trade-offs. Let's just do 30 now. So it's actually quite quick, and it also does well with Revit geometry. So I think this is like, yeah, 16 runs in 6 seconds. That's pretty good. We're seeing some interesting pattern here, which is worth exploring. Good question. So Lou asks, what's the difference between optimization and cross product? In cross product, it's just, cross product is like a way of randomizing, but no, cross product just gives us a structured way of looking at all of our options. So it takes each input and divides it into certain segments, and then it gets those. It's like doing a table of possible generations. Optimize does what the slides were showing you, where they optimize starts with a generation and it sees how it's doing, and then it slowly improves it with other generations until it gets with the optimal one. So yeah, I'm gonna do an example in a bit. So this is super interesting. Yeah, so you can see a pattern here, actually. So here we can see that a more expensive tile, which means a smaller tile, has a higher tile efficiency percentage. So the smaller the tile, for example, let's look at this generation here. It's kind of a medium-sized tile, and as you can see, the waste is kind of reduced. Let's look at this one here, for example. It's a very poor tile efficiency, of course, because you have a lot of waste here. Cool. All right. Let's look at the optimize for loop. So I'm gonna start again by the same type of study. And the optimize, we define the variables that we want to change. So let's say, yeah, let's use all of them. And then you can set the goals for your study. It's easier to start with 1 or 2 variables to optimize. So for example, let's say I want to minimize the area of trimmed tiles, and I want to minimize cost and maximum, sorry. Let's do this too. Let's say I want to minimize area of trimmed tiles, and I want to maximize the tile efficiency. So you can set constraints like the one in the example of the backpack. For example, your constraint can be 3 kilograms. So here, let's say that actually, yeah, we can define really constraints here with our inputs. They're more on the outputs. But we could certainly get through the size of the tile if we go back through the cost function. But let's just leave that empty for now. And we're going to do 10 generations of 20 individuals each. So this is less exciting to see because it takes a bit longer. But what you'll see is there will be a couple of generations showing up, and then some will disappear because they are not the best performing. And then some new ones will come, and so on. So essentially, this way of running it will show you the optimal way based on those constraints. And then you can start from there and build a new one to optimize it even further. So, so far we're in the second generation and it didn't change my model, which means this one was the better performing of the two pools. In the third one, it changed a little bit. Looks like this is the most optimal one so far. So while this is running, I'm going to show you the last example, which is basically a way to study stadiums or classrooms. So, because the principle is kind of the same. It starts by defining an arc. And basically the goal of this script is to understand what's the trade-offs between having a lot of people in there versus how connected are those people, which I'll show you how I measure it. And all of this is based on the shape. So there's a slider that we can change and modify to make this arc flatter or more rounded in terms of the center. So, okay, this is almost done. It created, yeah. So this here you have it. This is the optimal iteration it found. This is not always the best because you could actually estimate what's the most optimal by hand, but this is a pretty good average. And the way this is useful, and of course you're all free to use this example and make it even better. I just thought of it is instead of having a rectangle, why don't you like adding a facade? So if you have a really good computer that can run this calculation, instead of using these, just simple constant rectangle, you can fit in a facade, like a curved facade. And then the optimization will be quite insightful. Actually, that would be a great project if you guys want to go that path. Right. So now let's go to the third one, which is the stadium or a classroom. So yeah, talking about our goals is our goal is to find the best design for, let's say this is a classroom, like one of those law school types of classrooms, where you're really, and if you have been into one of these rooms, you haven't? Why? Why are you smiling? You're following? Yeah, like they have this type of U-shaped, yeah, I don't know why, like they're just fancy. Yeah, exactly. You don't feel connected there, right? But if you're wearing one of these, you kind of can see your classmates because they're all in a U shape, so you can see everyone, and that creates some sort of connectivity with your surroundings. So yeah, we'll cover that in a bit. So essentially, my geometry here, my starting geometry is a side length, which is the measure between the center point and the end of my rows. Then number of rows, of course, I have 4 rows here. And then the offset of my curve, which is, actually, let me put this in automatic. So the offset is how round my room is. Yeah, so the maximum is a pretty almost circular shape. And then the other end would be a more flat type of like an auditorium or something. And then my rows, of course, control how many rows I have. And the side length is basically the size of my room. So the smaller, the more compact it is. And there's a lot of like geometrical nuances in terms of slope, but we're not covering those at the moment. So I'm gonna make this a bit bigger with not that many rows, so it runs fast, at least at the start. So the way I created this, if you want to replicate it, is very simple. I started by drawing an arc and then giving it an offset depending the number of rows. So what this is doing is creating a range between a spacing that I defined as 6. So this could be 6 feet, meters, or whatever. And it creates a different number of rows based on this input. So this is my constant value. It creates the arcs. Then over here, I'm giving those arcs a height. So I'm progressively adding height as they move to the back of the room. And here what I'm doing is I'm creating lines every 9 units. So again, don't think of this as meters or feet. It's just any spacing. Basically, this 9 is the length of the comfortable length you need to work there to take class. If I make this number smaller, then I'll have more students per row. But basically, this kind of looks appropriate. You can change that. It's a constant, so this is pretty easy to change. And so this allows me to count how many observer points I have or seats. So in this case, I have 44 seats in total. That's one of the variables we want to, that's one of the outputs we want to maximize because we want to have as more students as we can. And down here, I'm creating these stadia kind of solids, which will give me a measure of the volume. And that's the second output I want to study, because I want to find the sweet spot between having connected students, which I'll show you in a second how I did it. I want to minimize the volume used because I guess this will be concrete or steel or materials or fill. So I want to minimize this volume while maximizing the number of students I can fit in that room. So here's where I created the connectivity index. So what this is very simple. What I did is flattened all the points in the ground of my students in a 2D environment, like a 2D plane. So I'm going to hide my my stadia here. Oh. Here it is. And I'm going to hide my points as well, the upper points. So here, I just have a bunch of, there you go. So these are my students' points, all projected into the ground. And what I'm doing is I'm defining a cone of sight. So basically, I'm taking each one of these points, and what I'm doing is I'm projecting 2 lines based on a 90-degree kind of span. So if I'm sitting here, what I assumed is I can see in a 90-degree kind of range. Whatever is out of that 90-degree range, I assume it's not visible in terms of connectivity. So let's take the first point in my classroom or the first seat and see how that cone looks like. So it's this person who's looking at the center of the room. So I started by projecting a line here in the center. So I'm going to show you guys that line. So this is the line. It has a cone of sight length, which I can modify here, depending on how big I want that to be. So if we're talking about a stadium, I don't think you feel very connected with the guys in the other end of the stadium, but maybe the ones in your same area will probably be, there'll be buzz and you'll feel connected with them. So then you'll probably reduce this length here. But for this classroom study, I guess you feel connected with all of them. So I'm just gonna make it very big. And then from this line, I rotated right 45 degrees and left 45 degrees. So this is what's happening here. I'm creating like side 1 and side 2 lines. And then I get the endpoints of all of those lines to create this polygon, which I call the cone of sight. So there's a cone for each one of the observers or the students. So let's look at the 25 student, for example. So it's this guy or girl here. And then the connectivity, I'm measuring it in the number of students that are within that cone. So you can count here, I can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, including the original. You can remove it if you want, but it's the same. So there's like around 13 students that are in connection with my student 25. And when I count the number of polygons, the number of points that are within each polygon, I can get a measure of the connectivity of the room. So I'm just going to show the mess of this polygon when you run it for all of them, but you got the idea. So it's doing for each one of them, it's counting how many students are inside. So to count them, it's basically an intersection. So you ask if they intersect, if each polygon intersects all of the points, and then I'm counting how many of them are being intersected. So out of my 44 students, remember, we have some that are only connecting with 1, and then some that are very, very well connected with 34. So then I do the average and I normalize it by the number of students, because when you have an insanely big room, you can be connected to a lot of people, but it's not as much as if you were only like with 10 people. Probably a connection is higher. So we're normalizing that rounding, and then here we have our metrics. The most straightforward is number of students, then the room connectivity index that we invented, and the fill volume of each one of those stadia that we created, assuming it's concrete or fill or whatever. We want to minimize this volume. And of course, all of these are checked as is output. So that's gonna make it work. So yeah, it's looking good. Now I need to make visible the geometry that I want to see in generative design. So I want to look at my volumes that I created. Oh, no, sorry, this is a number. This is the one I want. I want to see these volumes. I want to see these students here. And maybe the lines as well. Yeah, this is what I want to see. So I'm going to save this and click on all the properties we've talked about. Looks like there's no issues, so that's good. So there's something missing here. I'm going to try running it from. Okay. It was not letting me run the study because I had a previous one open. So I'm going to try again. Yeah, so I'm going to go to create study. And I can see the one we just created. And for this one, I'm just going to do a quick randomize of 20 generations. And I'm not going to change the size of the room because it doesn't make a lot of sense. I'm just going to leave it constant at 21. Let's make it a bit bigger. 25 units. It's constant. Well, it's good because it's running, so you can see. There you go. Okay. So yeah, as you can see here, the side length has been set as constant. It won't change. Number of rows are here. Offset, how round my classroom will be. Students, the fill volume that we want to minimize. Looks like most of them are pretty low. And the connectivity, which for me is the most important metric. So I can test hypotheses, for example. My hypothesis is the more curved the room is, the higher the connectivity. So if I have higher curve offsets, well, it looks like I'm not doing very well. Like most of my connectivities, if you track those blue lines, are going down. And that's actually quite interesting. So let's see what is making these high performing ones. So I'm going to clear my filters and I want to see this. So the most connected ones are the ones that have lower volume and actually the ones that are flatter. Okay, so the flatter, the better, apparently. Well, but then you can ask yourself, like, the better for who? For the average student? Who needs to feel more connected? The ones in the front, the ones in the back? Is there a priority? You should give a weight to, because for example, the guys in the back might be just messing around and eating food, or they don't need that connection, but the people in the front maybe will. So there's a bunch of functions and things you can add to your metrics. So yeah, just to wrap up, think in terms of this always. What's the objective of your study? What are the inputs? Mark them clearly. What's your model? The simplest form of your model. What are the outputs, which should be numbers? And then you interpret those results. Because if you don't interpret, you end up doing this. And Autodesk did this literally just to show their users how to interpret results. So generative design helps to, like, if you Google, like, if you Google generative design, it's very well known in the manufacturing industry for doing these kind of funky shapes that save material, that are lightweight, whatever. So people sometimes take this concept into the AEC without, just for the sake of doing it. So this last slide is just so you keep in mind that you have to interpret those results and don't just use generative design for the sake of using it, because of course the Golden Gate Bridge doesn't need that type of study. So just think what you're doing. And yeah, finally, there's some links. This presentation is uploaded, so you can see these links. The equivalent to generative design in Grasshopper is called Galapagos. It's easier to use, I think, but it's limited in terms of the design space. You can only optimize, you cannot randomize or cross product. It's a bit faster, but there's trade-offs. If you want to use that, let me know, and if or look at these videos. And yeah, that's the workshop. Thank you for showing up. Okay, Fred, I'm gonna stop the recording and help you.